In this chapter, we will be covering reaction rates and chemical equilibrium. Don't be thrown off by the cover of the book. This is just a newer edition of the book that we'll be transitioning to next semester. And um, and although it says chapter 10 here, it will be chapter 9 of your current textbook. But we will be looking at reaction rates and chemical equilibrium. So reaction rates is how fast or slow a chemical reaction occurs. And a chemical equilibrium is how the reaction is in balance. So many chemical reactions don't go to completion. You don't make all products. Many reactions you'll be making products and they will be in balance or in equilibrium with the reactants. And so we will be looking at how we can adjust chemical reaction rates, how we can make them faster and slower, and we'll be looking at how we can change the equilibrium, how we can favor the making of products or favor going back toward the reactants. So this is applicable to many um, uh, occupations that use chemicals. And in this case, we look at a neonatal nurse that deals with premature births. And so many times we have to give chemicals to patients. And so we need to understand how fast or slow these chemical reactions with these chemicals will occur. And if we need them to occur faster, how can we adjust that? If we need them to last longer times, how can we adjust that to occur? And it also, we need to understand on how we can affect the chemical equilibrium. So how can we favor products or favor reactants? And so we need to understand on how we can keep a balance in these chemical reactions. And so that's applicable to here because we need to understand on how we can keep the balance within human bodies. And we need to keep human bodies in balance so we can keep biological functions to occur properly. And so we need to know how we are going to affect them. And so we'll be using some mathematical equations. We'll be using some scientific notation. We'll be making sure to use the proper number of significant figures and balancing equations and using concentrations. And so we'll be using a lot of the previous concepts we have learned in the past chapters. And so a chemical reaction rate can vary depending on the conditions that it's in. Um, so we see here that we have many different examples. We have a banana that's aging, and so we see that it starts off as bright yellow and it's turning brown over time. We see the silver dish here, and it's tarnishing. And so that happens over time, and then we see just the aging process of a human and how that can change over time. And so many different reactions occur at different rates. They don't all occur immediately. And so it's important to understand, the speed of these reactions and how they can be adjusted. And so we'll be looking at how temperature, how concentration, and how catalysts affect the rates of these reactions. So in order for a chemical reaction to occur, the reacting chemicals or molecules must be in contact with one another. They must collide with each other. And when they collide, we want them to have and use the minimum amount of energy possible. And so in order for that to occur, they need to have the proper orientation. They need to be in the right spot at the right time in order for the reaction to happen. And so we see that in the top example, we see that the nitrogen molecule and the oxygen molecule are moving at a fast pace, and they are orientated properly. They're in the right spot at the right time. We have each nitrogen atom in the molecule touch each oxygen atom in the oxygen molecule, and we have that reaction occur. In all the bottom examples, we see that the one that has insufficient amount of energy, they're just not colliding fast enough. They're not going to stick. They're not going to collide with the right amount of energy. In the bottom two examples, we see that they're just not in the right place. They're not in the right orientation. They're not going to be able to have each nitrogen molecule touch each oxygen molecule, or each nitrogen atom in the molecule touch each atom of the oxygen in the oxygen molecule. And so it really just, in summary, the reacting molecules must be in contact with each other. They must collide. The correct amount of energy must be there, and they need to be in the right place at the right time. So we saw in the previous slide that, even when the molecules are orientated properly, they're in the right place at the right time, they need to have the right amount of energy. Because in order for us to make the products, we need to break the bonds of the original reactants. And so if you don't have enough energy to do that, then those bonds will break and you won't be able to make the product. And so those are right here, it gives us the three requirements in order for the reaction to occur. We need to have those reactants collide, they need to be orientated properly, and they need to have the right amount of energy. And so the energy that we need for a reaction to occur is what we call the activation energy. And so here we have what we call a reaction diagram. And this just basically shows how much energy is required for the reaction to occur. So in this reaction where we make nitrogen monoxide from nitrogen and oxygen gases, we see that there's a set amount of energy that we need. That's called the activation energy. And so what happens here is that the reactants have a certain amount of energy just by its natural state, and the products have a certain amount of energy, and there's a hump that we need to get over to get to the products, and that's what we call the activation energy. It's the amount of energy that it needs to be added from the original reactants in order to get to the other side toward the products. It's like if you are if you want to travel to a friend's house, you need to start, you're going to start at your house. That's your reactants. Your reactants is your house. And then you need to use some amount of energy in order to get to your friend's house, which is the products. And so that amount of energy that you need is the activation energy. It's the energy needed to activate or start the reaction. So we're not only concerned whether the reaction is going to occur by determining if we have enough energy or not, but we're also concerned with how fast is the reaction going to occur. A lot of times we want to speed up a reaction to be more efficient. Sometimes we want the reaction to go slower. We want to draw out the reaction. And so to measure the reaction rate, the rate of reaction or the speed of the reaction, is by looking at either how much reactant do we use up in a certain amount of time, or how much product do we make in a certain amount of time. And so the rate of reaction is just that change. The change of how much reactant do we use up, or how much product do we make in a certain amount of time, in that time change. So in general, reactions that have lower activation energies will go faster than reactions that have high activation energies. So that's just saying that reactions that don't need as much energy to get to the products are going to go faster. So it's like, like we have made the example before. If you're going to go from your house to your friend's house, if you don't need as much energy to go to your friend's house, you're going to get there faster. But if you need to use more energy, then it's going to be slower. And that reaction rate can change and can be affected by different factors. We can change the temperature, we can change the reaction concentration, or we can add a catalyst. And so these changes can affect on how fast or how slow the reaction occurs. So that's a key thing that you want to remember. So three things that can make a reaction rate change is by changing temperature, by changing reaction concentration, or by adding a catalyst. And so we're going to look at how these three factors can change the reaction rate. So temperature, as we have mentioned before, is a measurement of the kinetic energy, how fast molecules are moving. If if we have the reactants at a higher temperature, that means there's more kinetic energy. That means they're going to be moving faster. And if they're moving faster, then we're going to have more collisions. The molecules, the reactants, are going to hit each other more often. And they're going to, since they are going to be moving faster, they have more energy. And so they're going to collide with more energy. So we're definitely going to have enough energy to break those bonds and make those reactions occur. The second factor was reactant concentration. So when we have more material, when we have more molecules of reactants, then we are increasing our chances of those reactants to collide. Just because there's more basically stuff. There's more stuff in your reaction, so those things are going to hit each other more. So that stuff are the reactants, and those things are the molecules. So if we have more molecules, we have more molecules, there's a better chance of those molecules hitting each other, and so we're going to be able to make products more often, and they're going to make products more faster, and so we're going to increase our rate of reaction. And the last one that we mentioned was a catalyst. A catalyst is just a chemical that speeds up the rate of reaction. And what it really does, it provides an alternative pathway to it basically, you find a shortcut to your friend's house. So that shortcut will give you a new way in which you don't have to use as much energy to get to your friend's house. So it's going to lower the activation energy. So you don't need as much energy for the reaction to occur, because there's a shortcut, and we're going to take that shortcut because this catalyst provides that shortcut. And so a key thing here is that, looking at the energy diagram on the right hand side of the slide, we see that the energy of the reactants does not change. The energy of the products does not change. So going back to simplifying it, from going from your house to your friend's house, we still start at your house. We still start with those same reactants. And we're still going to your friend's house. We still end up with those same products. The only thing that changes is that we do not need as much energy to make the products. We found a shortcut. So we don't need to use as much energy to go to your friend's house. We found that shortcut. And so we have a lot of catalysts in our body. You probably heard of enzymes. Enzymes are just biological catalysts. And so these enzymes make reactions occur faster. And so catalysts and enzymes are vital, are important, are necessary for a lot of reactions to occur, and occur in the right amount of time that we need them. So here's a nice summarizing table of those three concepts. So in order to increase the reaction rate, we can do three things. We can increase temperature, we can increase the reactant concentration, or we can just add a catalyst. And so when we increase temperature, more collisions and more energy, and so we make products faster. If we increase the reactant concentration, we have more molecules of the reactant, so they're going to hit each other more often, so we have more collisions, so it's going to react faster. And when we add a catalyst, we don't need as much energy for the reaction to occur, and so it's going to increase the reaction speed. So here we have to, we're given a problem. We have an example chemical equation, and we want to figure out in A, B, C, and D whether these changes are going to make the reaction go faster or go slower, or it's not going to change anything. So in A, it says that we're raising the temperature. So we said before, if we increase the temperature, we're going to make those molecules go faster. They're going to collide more, and they're going to collide with more energy. So in A, that should speed up the reaction or increase the reaction rate. So that should be increased for A. B is removing oxygen. So we said before, in order to increase the reaction rate, we need to increase the reactants. But here, we're removing it. So if we remove it, there's not going to be as many collisions. And so then we won't have as many reactions occur. And so it's going to be slower. And so that will be decreasing the reaction rate. In C, we're adding a catalyst. When we add a catalyst, we decrease the activation energy. So we don't need as much energy for the reaction to occur. And so that means that the products will be made faster. We found a shortcut. We can get to the products faster. In D, it says lowering the temperature. So if we lower the temperature, the molecules, the reactants are going to move slower. They're not going to be moving with as much energy. And so we are going to slow down the reaction. And so that would be decrease the reaction rate. And so that's what we see here. And so that pretty much goes over all three of those different factors we have just discussed. So here's just another example of all those different factors, and we're just trying to figure out whether or not these different changes are going to affect the reaction rate or not. So if we decrease the temperature of the reaction, like we said before, we decrease the temperature, they move slower, less collisions, less energy, decrease the reaction rate. In B, we remove one of the reactants. So that's very similar to the example before. If we lose one of the reactants, we have less collisions, and so the reaction is going to slow down. And so that's going to decrease the reaction rate. C, if we add a catalyst, we are going to decrease the activation energy, so we don't need as much energy. And so that will speed up the reaction. In D, placing the reaction flask in ice. Well, if we place the reaction flask in ice, that means that the temperature of the environment is going to be lower. And so the temperature will decrease. And so that's very much similar to A. And so we decrease the temperature, they're moving slower, they're going to be having less energy, and so it's going to decrease the reaction rate. And then in E, increase the concentration of a reactant. And so if we add more reactants, then we are going to have more collisions, and so we will increase the reaction rate. So we see those answers here. You want to make one note in that the PowerPoints that I had posted had an error in C, and it said no change for some particular reason. But we have discussed that when we add a catalyst, we speed up the rate of reaction, And so just make sure you can make that change in your PowerPoint slides. So it was mentioned earlier that not all reactions go to completion. Not all reactions go directly and completely from reactants to products. Many times there's a balance, and we call that an equilibrium. There's a balance of reactants and products. And so we have the forward reaction, in which you go from reactants to products. But then we also have a reverse reaction, where we can go back from products to reactants. And so there's a balance, and it goes both ways. So at the same time you're making products, at the same time you're going back and making reactants. And so it's going in both directions. And we just call that an equilibrium. So when a reaction is able to go both in the forward and reverse direction, we call that a reversible reaction, because we can not only go in the forward direction, go from reactants to products, but we can also go backwards or in reverse and go from and make reactants from those products. And so that's what we see here when we react hydrogen gas and iodine gas. We can make hydrogen iodide gas, but that hydrogen iodide gas can decompose and go back and make hydrogen gas and iodine gas. And so when we have a reversible reaction, we use this double arrow. And the double arrow is just showing that, yeah, we go in the forward direction, but we also go back in the reverse direction, and they're in a balance with one another. So reversible reactions are occurring both in the forward and reverse directions at the same time. So now in this reaction of hydrogen and iodine gas, not only are we making the hydrogen iodide in the forward direction, but we're also at the same time going in the reverse direction and decomposing the hydrogen iodide back to hydrogen iodine gas. And there's two rates. There's a rate for the forward reaction, and there's a rate for the reverse reaction. So in this study check, it's asking us to write out the forward and reverse reactions for this reaction that's in equilibrium. So we're just basically breaking it up and showing, what the reaction looks like in the forward direction and what it looks like in the reverse direction. So we see here that in the forward direction, it's just what it's shown in the original equation. So you start with the same materials, the methane and the hydrogen sulfide, the CH4 and H2S, and it's going, and the products are the CS2 and H2. Then in the reverse direction, you just flip it. All right, you just use the products as your new reactant. So the CS2 and H2 are then written on the left-hand side of the reaction, the equation, and so those were the reactants, and then that's making the CH4 and H2S. So that's what it looks like in the reverse direction. But they're still both in balance. They're still both in equilibrium with one another. So reaction rates and chemical equilibrium are tied together and connected with this concept. So when you first put your reactants together, you're not going to have any product. And so at first, your reversible reaction is going to be slower. It's going to be really no speed because you haven't made any product yet. And your forward reaction, you had reactants to start with, and so that's going to be faster. Then over time, the forward reaction is going to slow down because you're making more products. And so you have less reactants to collide. And because you're using up those reactants, so there's less collisions, and you're losing, using the idea before, if you lose reactants, the reaction rate is going to slow down. And so that's what we see with the red line in the diagram. Over time, the forward reaction is going to slow down because we're using up some of those reactants. The reverse reaction is going to speed up because at first we didn't start off with any products. And then over time we have some products. And so as we make more products, then those products are able to go back in the reverse direction and make more reactants. And eventually we reach an equilibrium. And that is when the rate of the forward reaction is equal to the rate of the reverse reaction. So eventually they meet up and they become equal. So the rate of the forward equals the rate of the reverse. So when we reach equilibrium, there's not going to be any more changes in the concentrations of reactants and products. So what that means is that when we reach equilibrium, or when we reach that balance, there's the amount of products and reactants does not change. So if we look at this reaction diagram, the red line represents the reactants. And that's what we start off with. We start off with the reactants. And so you see reactants is high up in the chart. Then over time, we use those reactants to make products. So the reactant line goes down. And then the product line, the blue line, is going to go up. And then eventually, we reach an equilibrium. We reach a balance. And that is when the rate of the forward is equal to the rate of the reverse. So we do not change the amount of reactants and products. But do not confuse that with nothing occurring, because the reactions are still occurring. The forward reaction is still occurring. The reverse reaction is still occurring. But they are happening at the same speed. And so we can use the example of, let's just say we have all of the students in our class inside of the classroom. That's representing our reactants. Everyone, that's where we're all starting. And if we, let's say, if we're going to move people outside of the classroom, that represents making products. So at first, we have a lot of people moving into the hallway. So we're losing our reactants. We're losing students in the classroom. But we are gaining people in the hallway. We're gaining products. But over that time, we are going to reach a point where it reaches a balance. And so we'll have a set number of people inside the classroom and outside in the hallway. But when we reach that balance, people are still going to be moving. When we have one person go back into the classroom, we'll have one person go out of the classroom back into the hallway. That represents our equilibrium. So there's a balance. Every time someone goes back in the classroom, we have one person move back in the hallway. And so we still have people moving, we still have reactants and products still being made, but they're occurring at the same speed. Every time we gain one, we lose one. And so that's what the balance is. That's what the equilibrium is. Here's a visualization of the concept of reaching equilibrium and relating that to the rate of the reaction. So in the left, at time 0, all we see is the we see the purple molecules and we see the white molecules. Then in the next one, we see that, oh, we made some combination. We made a couple molecules that has one white atom and one purple atom. And so what that represents is the reactants making products. So at first, all we start off with is the reactants. Then we're making some products. So we lost some reactants. So in using the numbers, we start off with 8 molecules of reactants and 0 molecules of products. Then in the second picture, we start off with 6 molecules of reactants and 2 molecules of products. Then as we move along through time, we're making more reactants, making more products, in at 2 hours. And when we lost some reactants, we made some products. And so now we have 4 molecules of reactants and 4 molecules of products. Then in 3 hours, we look at that and we made some more products and we lost some more reactants. So we ended up with 2 molecules of reactants and we have 6 molecules of products. Then in the last picture, at 8 hours, we have those same numbers. And so we still have 2 molecules of reactants and we still have 6 molecules of products. So the reaction rates starts off with going faster in the forward direction. At time 0, it's going a lot faster in the forward direction because we're making products. At time 1 hour, we are still making more products. We're still faster in the forward direction, and our reverse direction is slower. And so we see an overall change in making more products. Then at 2 hours, our forward reaction is still faster. And so we're still making more products. So we see more products being made, and we see a greater loss of reactants. Then when we reach 3 hours and 8 hours, those numbers are in balance. They're not changing. And so we have reached that balance. We have reached the equilibrium. And so the reaction rate in the forward direction is the same as the reaction rate in the reverse direction. So we still are making reactants, but we're also making products, and they're happening at the same speed. So we're still making purple and white molecules, but we're also making the purple by themselves and the white by themselves. So we're still making the combination molecules, the white and purples, but we're also making the molecules that have 2 purple atoms and the molecules that have 2 white atoms. And so it's just like the example of people going in and out of the classroom. They're going in and out the same speed. Every time we gain one, we lose one. And so that's what is being represented here. So here we have a reaction of the hydrogen gas and iodine gas making the hydrogen iodide. So the forward reaction is the hydrogen gas and iodine gas making the hydrogen iodide. And the reverse reaction is the hydrogen iodide decomposing to hydrogen gas and iodine gas. And so when we have the hydrogen iodide building up from the forward reaction, then the reverse reaction can occur, and it's going to occur faster because we have more products being made, and so then we can go back and make more reactants. So over time, the reverse reaction speeds up, and the forward reaction slows down. And so when we reach that equilibrium, no more changes occur. No more gaining or losing products. We have that concentration staying the same. There's still reactions occurring, but they're occurring at equal rates. The forward and reverse reactions are occurring at the same speed. So we're every time we gain one, we lose one. Every time we gain two, we lose two. And so it looks like nothing's occurring, but there there's still reactions happening. They're just canceling each other out, basically. So here it's asking us to fill in the blank and trying to figure out if there's any changes or if there's no change or if they are equal or not equal. So in A, before the equilibrium is reached, the concentrations of the reactants and products. And so this one, the reactants and products before equilibrium are changing. All right. So before we have reached equilibrium, we're going to be losing our reactants and making more products. And so those concentrations change over time until we reach equilibrium. So when we reach equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So we'll look at it in another example here. So if we have sulfur dioxide, SO2, in, uh, in contact with oxygen gas, O2, they are going to react and make SO3, sulfur trioxide. And they're going to react until they reach equilibrium. And when they reach equilibrium, they'll be still making SO3, but they'll also be going back and making SO2 and oxygen gas. So that SO3 will decompose. It's the same thing if we start off with just sulfur trioxide. If we just had SO3 in a beaker and we let that sit out, it's going to decompose and make SO2 and oxygen gas until they reach equilibrium, and it will make it can go in both directions. So it doesn't matter where technically you start off with, they will both reach an equilibrium where you have SO3, SO2, and O2 all in balance with one another. So it doesn't matter what you start with. So it's asking us to fill in these blanks with these different choices that goes along with our concepts. So reactants form products in the blank reaction. So if we start off with reactants and go toward products, that is the forward reaction. In B, at equilibrium, the reactant concentration, and that should be does not change. So at equilibrium, we reach that balance. So we should reach a set amount of reactants that is in balance with the set amount of products. So it's not going to change. And then in C, products form reactants in the blank reaction. So if we have products going toward reactants, that's backwards. And so that's reverse reaction. And so we'll see that here filled in. So when we are at equilibrium, there is a set amount of reactants and a set amount of products. And comparing those reactants to products is our equilibrium constant. So an equilibrium constant for a reversible reaction uses the concentrations of all the reactants and all of the products. So remember, concentration is measured in moles per liter or molar. And those concentrations are put in the equation that you see on the bottom of the slide. So it's the products over the reactants. So the products So each of these concentrations has to be raised to the power of their coefficient in the balanced reaction. So um, each of these concentrations uses the exponents from the balanced equations. And so that those coefficients in the balanced equations will be used as exponents in the chemical equilibrium expression. So we will be multiplying the products and multiplying the reactants, each of which of those concentrations are raised to the power of the coefficients used in the balanced equation, and its products over reactants. I'm not going to ask you to memorize this chemical equation. Not chemical equation, but you won't be asked to be memorizing this mathematical equation. It will be given to you, but you need to know how to use it. So first, we're just going to start off by writing the chemical or the equilibrium constants um, using balanced equations. So here we are given a balanced equation. We're given a balanced reaction. We start off with carbon monoxide and oxygen to make carbon dioxide. And the equation is already balanced for us. So what we want to first do is write out the balanced equation. So luckily this one is done for us. Then in step 2, we want to write out the equation. So its products over reactants is equal to the equilibrium constant, symbolized by Kc. And then we can put in the concentrations of the products and reactants. So the product is on the right-hand side of the chemical equation. So the product is carbon dioxide. So carbon dioxide goes in the numerator. We use those brackets to symbolize concentration. The reactants are on the left-hand side of the chemical equation. And so carbon monoxide, CO, is one reactant, and oxygen gas is the other reactant. So those go in the denominator of the equation. Then, in step 3, we can use the coefficients from the balanced equation to complete our mathematical expression. So the carbon dioxide, our product, has a coefficient of 2 in the balanced equation. So that 2 will be used as an exponent for the CO2 concentration in the numerator. The carbon monoxide, the CO, the reactant, has a coefficient of 2 in the balanced equation. So that 2 will become the exponent for the concentration of CO in the denominator of the expression, the mathematical expression. And since oxygen gas, O2, has a coefficient of 1, then we don't need to put an exponent after O2 in the equilibrium constant expression. So the next step it would be to actually calculate the equilibrium constant, the Kc value. And so here it's just doing the same step we just did in the previous slide, trying to figure out what the expression would look like, and then we just plug in the numbers that we have from the if we have a problem that it gives us the concentrations, or if we have an experiment, to use those numbers from the experiment. So here, if we're looking at the reaction of hydrogen gas and iodine gas in equilibrium with hydrogen iodide gas, we would write the equilibrium constant, the Kc, as the product goes in the numerator, so the HI concentration goes up on top, and because it has a coefficient of 2, it has to have the exponent of 2. Then the reactants go in the denominator, the hydrogen gas, and since in the balanced reaction it has a coefficient of 1, then there is no exponent. That would be multiplied by the concentration of iodine gas. And since in the balanced equation there's no coefficient, so basically 1, then there's no need for an exponent because the exponent would just be 1. So if we were given the concentrations of those chemicals when they are in reaction with one another, then we would just use those concentrations and put them in our formula. So here it's showing us where those numbers would go. The product, the HI, was in the in the numerator. So the concentration of HI is equal to 1.04 in this case. And so that would go in the numerator. And you have to remember that that number should be squared because of the balanced equation. The denominator would be the product of the two reactants. The H2, the hydrogen gas, had a concentration of 0.1 molar. That would be multiplied by the concentration of I2, which was 0.2 molar. And so you put that in your formula, in your equation, and you get a equilibrium constant of 54. And so these concentrations are when the reaction is in equilibrium for this particular reaction in this particular environment. And so this equilibrium constant is a constant. So by definition, a constant does not change. So the equilibrium constant should be 54 for this reaction, no matter how much reactants or products you start with. You still will end up with a equilibrium constant at 54 because when a reaction's in balance, it's not going to change. So the equilibrium constant will not change. But there is a but. It can only change if you change the temperature. So the temperature can change the chemical equilibrium. So that's why I said under the same conditions. So a equilibrium constant is the only factor we need to be concerned with by changing the equilibrium constant. But other than that, the chemical equilibrium constant should not change. So we see that in this chart here. In these three different experiments, 1, 2, and 3, we start off with different amounts of hydrogen and iodine gas. And because of that, we have different amounts of hydrogen iodide, our product. But when we use all of these reactions, when these different experiments, experiment 1 is at equilibrium, experiment 2 is at equilibrium, experiment 3 is at equilibrium. They have different numbers because they started off with different amounts of material, but when a reaction that is at equilibrium, they're always going to be in balance, and so that balance is not going to change. You're always going to have the same amount of reactants compared to products, essentially. And so here, when we use all of these numbers, our equilibrium constants don't change because they're all in balance. So when we're at balance, when we're in equilibrium for this reaction, our equilibrium constant should always be 54 at this particular temperature. So here is just a flowchart of showing how to calculate the Kc value. So we want to make sure that our reaction is balanced. Once we have it balanced, we can write out the, state what we're given. We can then write out our Kc expression, our equilibrium constant expression, by just using the chemical formulas. And then once we know that, once we have that, then we can go back and plug in the actual concentration numbers to calculate the equilibrium constant. So here we look at the decomposition of dinitrogen tetraoxide, and that's going to decompose to nitrogen dioxide. And it's asking us to calculate the Kc, or equilibrium constant, at 100 degrees Celsius if the reaction has these two concentrations at equilibrium. And they give us the concentrations here. So we can see that the chemical equation is balanced, so we don't need to balance it. We want to now state what we're given. So what we're given is the concentrations of the reactants. We have the concentration of dinitrogen tetroxide, and we have the concentration of nitrogen dioxide. And we need to get the Kc, the equilibrium constant. And we're also going to have to use that chemical equation. So now we can write out our Kc expression, our equilibrium constant expression. So it's products over reactants. Our product is on the right side of the equation, so that is nitrogen dioxide. So that's going to go in the numerator. The nitrogen dioxide, the NO2, has a coefficient of 2. So that's going to be our exponent for our numerator, for the concentration of NO2. The denominator is the reactants, our reactants on the left side of the chemical equation, and that's N2O4. And so the denominator is going to be the concentration of N2O4. N2O4 in the balanced reaction does not have a coefficient, so it does not have an exponent. So now we have step 2 completed. We wrote out the Kc expression. And so we can move on to step 3 by just plugging in our numbers. So it said that our concentration of NO2 at equilibrium is 0.31. And it says that our equilibrium concentration of N2O4 is 0.45. So we put the 0.31 in the numerator, put the 0.45 in the denominator, and we get an equilibrium constant Kc of 0.21. Here, we'll do another example of looking at the chemical reaction that we've seen throughout this presentation of hydrogen and iodine making hydrogen iodide. One thing to note is that they keep stating the temperatures. We're not going to be using these temperatures in any calculations here, but they are stating that chemical that temperature because the equilibrium constant is dependent on the temperature. So they give us our concentrations of our reactants and products. So our first step is to just state out what we know. So we know the concentrations of each reactant and the product. We know that we need to get the equilibrium constant, and we have the balanced reaction. So we're going to use all of these things to figure out the Kc. So our next step is to write out the Kc expression. Kc is equal to products over reactants raised to the power of their coefficients. So the product is Hi. It's on the right side of the equation. So that's going to be our numerator. That's going to go on top. The coefficient of that chemical equation is 2. So that 2 becomes our exponent. There's no other product, so we can move on down to our reactants. Our reactants are denominators. And so the concentration of H2 will be one of the denominators. And so because in the balanced reaction there is no coefficient, or it's just the coefficient is 1, then the exponent is 1, so we don't need to write it. Our other reactant is iodine. And so we have to use the concentration of iodine. And so that is in the balanced equation, it has an exponent, coefficient of 1. So our exponent is 1, so we don't need to use that. Then we can just plug in our numbers. It says our concentration of hydrogen iodide is 0.35, so we put that in our numerator. It says that each of the concentration of hydrogen and iodine is 1.2, so we put 1.2 in each of the concentrations. And so then we just put it in our formula and calculate our value of 8.5 times 10 to the minus 2. So now we want to use our equilibrium constants. So what conditions are going to make more products or less products? How can we make a larger equilibrium constant? Right? So if we have a larger equilibrium constant, that means we have more products. Our products side, our numerator is larger, or our reactants are smaller. So we want to be able to also predict the reaction, predict what's going to happen to the equilibrium constant. What happens if we change something about the environment that the reaction is in, and how does that affect the equilibrium? How can we predict what's going to happen? So our value of Kc depends on the amount of products and the amount of reactants. And so our value of Kc can be large if we have more products than reactants. Our Kc can be small if we have more reactants than products. The value for Kc does not affect how fast the equilibrium is reached. The only thing the Kc tells you is the amount of products compared to the amount of reactants. So when we have a large Kc, that means that we had more products formed from the forward reaction. And so here we look at this example of the SO2 and O2 gas in equilibrium with the SO3 gas. So they write out the reaction, the equilibrium constant. And so the equilibrium constant is 3.4 times 10 to the 2. So that means that it's 340. So that is a larger number. So that means we have more products than reactants. That's what it's saying. So a large Kc, we have larger amounts of products and less reactants. It's just the opposite is true. If we have a small Kc, that means that we have a lower concentration of products and a higher concentration of reactants. So if we look at the example here of nitrogen gas and oxygen gas reacting to make nitrogen monoxide, we write out our equilibrium expression, and we get the equilibrium constant for this reaction is 2 times 10 to the minus 9. So 10 to the minus 9 is a very small number. So that means we have very few products and a lot more reactants. Here's just a bar graph showing that relationship. It's using the same chemical reaction in the previous slide of N2 and O2 making NO. And we see that initially we start off with only the reactants. We start off with only nitrogen gas and oxygen gas. Then when we look at the bars for when it's at equilibrium, the N2 and O2 don't move very much. They go down a little bit but they don't go down very much. And the NO bar goes up a little bit. And so we have a lot more reactants compared to the products. We did not make very many products when it's at equilibrium. When the equilibrium constant is close to the value of 1, that means that there is a relatively equal concentration of reactants and products at equilibrium. So 1 is like the middle ground. An equilibrium constant, a Kc of 1, basically says that you have about an equal amount of reactants and products. Then when we have values much smaller than 1, we have a lot more reactants than products. We have mostly reactants. If we have a very large equilibrium constant, a very large Kc, that means we have a lot more products than reactants. And so here is just an example showing different reactions and their known equilibrium constants, and whether or not there's mostly reactants or products in that are present at equilibrium. So when we have equilibrium constants that are greater than 1, which are the cases for the first top 3 reactions, that means that we have mostly products. In the bottom 2 reactions, we have equilibrium constants less than 1. So that means we have mostly reactants. So now what we would like to try to do is try to use the equilibrium constant to figure out how much material, how much of a certain reactant or product is there or present when the reaction reaches equilibrium. So here we have a chemical reaction of carbon dioxide and hydrogen gas in equilibrium with carbon monoxide and water. And they give us the equilibrium constant of 0.11. And they also give us the concentrations of 3 of the 4 compounds or molecules present at equilibrium. And they want us to determine the equilibrium concentration of carbon monoxide, the CO. So we want to first write out what we are given, what we need to get, and the chemical equation, because we're going to have to use it. So the chemical equation is already balanced, and so we can write out the Kc expression. Kc is equal to products over reactants. So the products are on the right side, so it's CO on the numerator, and CO has a coefficient of 1, so we don't need an exponent. And then we also have water as a product. Doesn't have a coefficient, so that has an exponent of 1, so we don't need to write it. Our reactants go on the denominator on the bottom, and we can we put CO2, carbon dioxide, in the denominator, and so it in the balanced reaction is a coefficient of 1, so it doesn't need an exponent. And then hydrogen gas is a reactant, so that goes in the denominator, and that has a coefficient of 1, so we don't need an exponent. And so it's also showing that since we're looking for CO, the concentration of CO, we can rearrange the mathematical expression to solve for CO. And so all they did was cross multiply and divide to get the concentration of CO by itself. And so when I will make a video on how you can do that, um, so it's a little bit more clear because they don't really show that here. So once you have rearranged the expression to solve for CO, then you can just plug in your numbers that are given to you in the problem and solve for the concentration of CO. And that's what's done here. So the trick in this type of problem is rearranging the equilibrium constant expression to solve for CO. So in this check, they want us to indicate whether or not there is more reactants or products when it is at equilibrium. So in A, all we have to do is look at the Kc value, and we have 1 times 10 to the 95. That's a huge number, a very large number. And so that means that we have a Kc much larger than 1. And so that case, we should have a very large numerator for Kc, and that means that we have a lot of products. In B, we have 1.8 times 10 to the minus 7. That's a very small number. So that means that we have a lot more reactants than the product. And so that's what we see here. All right, so Kc in A is large, products are favored, we have a lot more products. In B, Kc is small, reactants are favored, a lot more reactants. In this one, it's asking us to calculate the amount of PCl5 in this balanced equation, in this reaction. And so they give us the concentrations of the two products, and it gives us the value of Kc. And so our first step is to write out what we know. We know the product concentrations, we know the Kc value, and we know the balanced equation. Our next step is to write out the Kc value and then the Kc expression, and then rearrange it to solve for the quantity that we want to know. So first, Kc is equal to reactants over products over reactants. So our two products are PCl3 and Cl2. Both of those have a coefficient of 1, so we don't need any exponents in the expression. PCl5 is our only reactant, so that goes in our denominator, has a coefficient of 1, so we don't need an exponent there either. Then we cross multiply and divide to solve for PCl5 concentration. Then lastly, we substitute in all the numbers, and we find that the PCl5 has a concentration of 0.24 at equilibrium. And now the last thing we'll look at is how we can shift the equilibrium. What happens when we change the conditions that the reaction is in? And so the example that they give here is our blood. All right, we have hemoglobin in our blood, and its job is to carry oxygen. And so when people live at higher altitudes, they typically have more hemoglobin because they need more hemoglobin because there's not as much oxygen at higher altitudes. And so they need more material to carry that oxygen, be able to have more material to deliver that oxygen to the rest of our bodies. So when the conditions of a reaction at equilibrium are changed, then the forward and reverse reactions are no longer equal. So when you change the conditions, when something's at equilibrium, you disturb that balance. And so then the reaction has to shift, has to change to get back to balance. So when you so this is what we call Le Chatelier's principle. And in his principle, he says that when you add a stress to a reaction at equilibrium, the system responds by changing the rates of forward and reverse reactions to relieve that stress. So it's kind of like if you get stressed out at your job, then you're going to respond to try to relieve that stress. Maybe you'll work faster, or maybe you go talk to a coworker. But you're gonna do something to relieve that stress because you don't want to stay stressed out. Well, the same thing for these chemical reactions. These chemical reactions don't want to. When you put a stress on it, it's going to react in some way. And so the way that they react is either going in more forward or going back in reverse faster. So you're going to change the reaction to get back to equilibrium because that's what it wants. It wants to reach a balance. And so the example here, they're just kind of visual, so you can visualize what's going on. Let's just say you have two tanks connected to two tanks of water connected to one another. So when they're in balance, the levels of those tanks are equal. But if you add a bunch of water to tank A, then what happens is that we're going to move that water from tank A to tank B in order for it to get back to balance. And that's what's going on here. That's what basically Le Chatelier's principle is. You're adding a stress to the balance, and so it changes, and it goes in, the reaction changes, will go more in one direction in order to reach and get back to equilibrium, in order to get back to its balance. So here, back to the same chemical equation of hydrogen gas and iodine gas in equilibrium with hydrogen iodide. One way we can affect equilibrium is by adding more of one of the reactants, like we did before. We in the picture in the last slide, we added more water, and so the water shifted to go back to balance. So that's what's happening. That's what's going to happen here. When you add H2 to the reaction, then you are going to make the reaction go in the forward direction. You want to relieve. When we add H2, we have too much H2 now. We're not in balance anymore. There's too much hydrogen gas. So we need to go and make hydrogen iodide to get rid of some of that extra hydrogen to get back to balance. And so when you add any reactant, then you're going to shift the reaction toward the products. And that's what's showing here. The purple molecules are the iodine molecules. The white molecules are the hydrogen molecules. And then the purple and white molecules together are the hydrogen iodide. And so when you add in some of those white molecules, the hydrogen, then that's going to make more, you're going to have too much of those white molecules. And so you're going to force a reaction between the hydrogen and the iodines to make more products, more hydrogen iodide, more of the purple and white molecules. The opposite is also true. If we remove hydrogen gas, that means that we are not in balance anymore, and so we lost some reactant, and so it's going to want to be replenished. You don't have enough hydrogen gas to be in equilibrium anymore. So the reaction is going to shift in order to go back to equilibrium to have enough hydrogen gas. So when you do that, you're going to lose some of your HI and you're going to make some more hydrogen gas. And so the reaction shifts toward the reactant, toward the left side of the equation. Similarly, if we add a product, if you add HI, you have too much product now. And so you have to get rid of some of that product and make some reactant. So if you add a product, then you're going to favor the reverse reaction to make more of the reactants. And so when you add a product, you're going to shift the reaction toward the reactants to get back to equilibrium. And then if you remove some of the product, if you remove some of the HI, again, now you don't have enough HI. And so the reaction is going to shift and make more HI to get back some of the HI that was lost. And so you are going to favor the forward direction. And so you're going to make more product and shift the reaction to the right. So here is a table that shows all the different possibilities of increasing or decreasing any reactant or product. If you increase H2, you increase the reactants, you shift the opposite way. You're going to shift toward the products. If you decrease H2, if you decrease the reactants, then you're going to shift toward the left to get more reactants back. Same thing with the other reactant, the iodine. If you increase iodine, you have too much iodine, you're going to shift to make more product. You're going to shift to make more products in HI. If you take out some I2, then you need to replace it. So you're going to shift toward the reactants. You're going to make some more iodine back by getting rid of some of the products. So you're going to shift the reaction to the reactants. If you increase the product, increase HI, you have too much HI now, and so you need to get rid of it and make some more reactants. If you decrease HI, then you don't have enough HI, you need to make more, or you're going to shift toward the products. We mentioned the concept of catalysts and how catalysts speed up chemical reactions, and they do that by lowering the activation energy. And so when you lower the activation energy, you increase the rate of the forward and reverse reactions. The key thing, though, is that the catalyst does not affect the equilibrium mixture. It does not change how much reactants and products are going to be present at equilibrium. The only thing that it changes is how fast it gets to equilibrium. It makes the reaction get to equilibrium faster, but it does not change what the equilibrium is. You do not change the amount of reactants and products that are present at equilibrium. You only change the time it takes to get to that balance. So what we will look at now is how a change in a volume for a gas mixture can affect the equilibrium of the gases in the mixture. Because we have mentioned before that gases do not have a definite volume. They take up the space, as much space as you give them. And so if you change the volume of the gases, if you change the volume of the container that the gases are in, then you change the concentrations of those gases. If you change, we said before, concentration is moles per liter. All right, moles per volume. So we're not changing our moles. What we're changing is our liters, our concentration. So if we decrease the volume, that means our denominator of our concentration expression goes down, and that increases our concentration. So basically, you have you have the same amount of gases in a smaller space. They're more concentrated. So if we decrease volume, we increase concentration. And so the system is going to shift in the direction of smaller number of moles if we decrease the volume, because there's just going to be less space. And so if we have less space for those gases, then we want to have less gas in less overall gases. And so if we decrease the volume, we're going to shift the reaction toward the side of the reaction that has the least number of moles of gas. So if we look at this example here, we have two gases on the left side of the equation and one gas on the right. In the balanced reaction, we have 3 moles of gases on the left and 2 moles of gas on the right. So the product side, the right side of the equation, has less moles of gas. So if we decrease the volume, we're going to shift the reaction toward the side that has less moles of gas, which is the product, which is the right side of the equation. The opposite is also true. If we increase the volume of the container that the gases are in, it's going to favor the reaction, the side of the reaction that has more moles of gas. So in this balanced equation, the reactants have 3 moles of gas, the product has 2. So if we increase the volume, it's going to favor the left side, the side that has 3. 3 is greater than 2, so we favor the side that has more moles of gas. And so we shift toward the left in this case. And so this is just kind of showing the idea behind the change in volume. And so with less volume, a decrease in volume, there's less space for those gas molecules. So it wants to have less number of moles of gas. And in the bottom picture, we're increasing the volume. So we have more room to spread out. These gases have more room to spread out, so they favor the side that has more moles of gas. So we can relate this in terms of this changes in equilibrium in terms of hemoglobin, oxygen, and then what we call oxyhemoglobin when the oxygen binds to the hemoglobin. So when there's a high concentration of oxygen, the reaction shifts toward the direction of oxyhemoglobin. Right, we have a lot of oxygen gas, then we're going to be able to have this oxyhemoglobin. But when we have less oxygen gas, when we are losing that oxygen gas, maybe because of the higher altitudes and such, then the reverse reaction is going to occur. We're actually going to release oxygen from that oxyhemoglobin, and you'll be losing oxygen. And so we see that in this expression here. So at normal atmospheric pressure, oxygen diffuses into the blood because we have the right amount of oxygen. But if we go too high in altitude, then there's less oxygen gas. And so we're not going to have the equilibrium is offset and it's stressed. And so a person is not going to be able to receive as much oxygen. And so that's why you see sometimes people who are into high altitude climbing and stuff like that. Because sometimes they need to wear those, bring those oxygen masks so that they an oxygen tank, so they'll be able to have the proper amount of oxygen released to their blood. So, according to Le Chatelier's principle, when we decrease the amount of oxygen, we are going to favor the reaction shifting to the left, which uh, basically depletes the amount of oxyhemoglobin that's used to transport the oxygen throughout our body. And so the reaction is shifted to release oxygen to the atmosphere. So we're losing oxygen that's in our bodies. So here is a nice summary of all the changes that we've discussed. Now, there is a temperature section, but we didn't and don't have to go over endo and exothermic reactions. So we are not going to cover on how temperature can affect the equilibrium based on those temperature changes. So you can ignore that part, but the changes in concentration, volume, and catalyst will need to be known. And so this is a nice summary chart to know. So we'll go over these examples and figuring out if these changes are going to affect, if it's going to shift toward the reactants or the products. So in A, it's asking if we add more NO, are we going to make more products or shift toward the reactants? So adding NO is a product on the right side, so we're adding a product, and so now we have too much product, so we need to shift back to the left and make more reactants. So that A is 2 toward the reactants. B, we will skip. C, if we remove oxygen, that means we don't have as much product as we need, so we need to shift to make more product. And so that's going to be 1 toward the products. And D, increasing the volume. So in this one, we need to figure out how many moles of gas we have in the reactants and products. So on the left, we see we have 2 moles of gas in the reactants and 2 plus 1, so 3 in the products. So we have 2 in the reactants, 3 in the products. So if we increase the volume, we favor the side that has more moles of gas. And so that is the side with 3 moles of gas, the products that has more. So D would be choice 1 toward the products. And then removing some NO. So that would be NO is a product, and so we would be removing a product, so we need to replenish that, and so we would shift toward the products to replace it. So toward the products 1 for E. And so that's what we see in these cases.